Good day, friends. Right now, let's try to solve this problem, which is a chain with mass of 100 grams is placed on a vertical cylinder with a radius of 20 centimeters. The tension force in the chain is 0.3 newtons. Find the coefficient of friction between the surface of the cylinder and the chain when the cylinder rotates around its axis with an angular velocity of 4 radians per second, the chain slips off. Okay, so basically what we have here is mass of the chain. This is m, let's call it m. A radius of a cylinder, which is, m. Or, what else? Tension force. Yeah, tension force. This is important. We also have T. We need to find coefficient of friction, which is unknown thing, and we need to find it. Yeah, it is here. Find coefficient of friction. What else? Yeah, angular velocity. This is here. So we have angular velocity 4 radians per second. I will not apply numbers again and again all the time. Yeah, because the main part is physical part. The maths is for the rest. And we need to look at this thing. The chain slips off. But it slips off if when the cylinder rotates around its axis with an angular velocity of 4 radians per second, the chain slips off. So this is really important. We need to understand this situation. What does it mean? If this condition is made, the chain slips off. But in fact, it must be written, the chain starts to slip off. It starts. Why is this important? Because when it starts to slip off, it's not the same thing as it slips off as usual. Why? Because when the thing slips off, for example, we have this image of our problem. This is a cylinder, and we have here, let's say, the rubber band, or as in this problem, this is a chain. This chain. If it slips off as general, it just goes down. But if it starts to go down, it's not the same thing, because at the instant when it starts to go down, it's still acceleration 0. So in fact, I can write it down that acceleration down is 0. So it just is going to fall, but it's not falling. Okay, this is really important, because if this acceleration is not 0, then our problem might have very different answer in the end. Okay, so this is the image of our problem. We have a cylinder. This red thing, maybe even the blue one. Let's call it like this. Let's draw it like this. Is our chain, which is going to slip off if this angular velocity reaches 4 radians per second. Okay, what can we do? Let me take this band. Let's copy it and put it somewhere here, and let's work with it personally. It's the view from the edge, from the side, let's say, not from the edge, from the side. And this is the center, right? Let's draw some forces which are acting on this chain, but not entirely. Let's choose some point. Let's choose some point like this. And this is small part of the chain which has mass of dm and length of dl. Okay, this is really important. It has mass of dm and length of dl. This is really small, very small part of the chain. And the forces which are acting on it so it's going to go down. It's definitely force which is acting downward. It's the weight, but we need to remember that it's not just mg, it is dmg, because this small part, we're considering this small part, and the force which is going to oppose it is going upwards, right? I hope that you can imagine it. So it's something like this. So if this thing is y, x is something like this, this is x direction, this is x. Okay, good. So dmg is acting vertically, and friction force is also acting vertically. This is friction force. Okay, so let's get rid of it. It's not important right now. So what is important? There is a force which is acting outward in x direction, and we know that this is n, reaction force on the normal force on our band from all the sides, basically. But if we consider only this small part, n would be exactly perpendicular. What about the force which is pulling inward to the center? Because we know that if this thing is rotating, there is centripetal acceleration, there is AC inside, and I can say that there is definitely some force pulling us inward. But for right now, let's try to analyze this problem from the top. Let me draw here the same chain, but from the top view. So it's got to be something like this. Okay, let me put it here. Good. So it's probably the same problem that we already worked with, but if you didn't watch previous videos, then let me remind you. Let's take this small part dm. As I said before, this small part is called dm. And if I just take these two sides of dm, this would be radius, this is radius. We know that any part of this circle is just radius, right? So this is not important. And what is important, we can just take this part as alpha or anything. It depends totally on us, but this would be a little bit uncomfortable for us to demonstrate. Instead, I would zoom in, and then it would look something like this. So it will look something like this. So in fact, it's still this small part, but it's the view if we zoomed in, and in fact, if you take this small part, you can see that this part is very smooth and very flat. The same thing happens when we stand on Earth. So we are really small human beings standing here, and from our perspective, it might seem like it's very flat, but in fact, in the large scale, it's sphere, geoid. Okay, this is really important. So this is important to understand that this part, in fact, is something like this. Yeah, so it is, it is very smooth. This is a flat part of the dm. This part is dm, which has the length of dl. So this has the mass of dm and length of dl. So let me call this part dl, small part length. Okay, so this is r, this is r definitely. What else? Let me divide it into two parts like this. Let me choose this part as alpha, this part as alpha, and I definitely know that if this is small dm, this is small part of the chain, yeah, this part. I know that another parts, like which is standing like right here and right here, here and here, they're pulling on my dm, right? They are pulling, and that's why I know this thing has a tension force. So they are pulling it like this, yeah, and like this. Okay, and definitely I know that there are components in this situation, horizontal component, vertical component, horizontal component, vertical component, and I know that this thing is 90 degrees, 90 degrees, this is 90 minus alpha, this is alpha, because this is 90 degrees as well, this is 90 degrees as well, 90 minus alpha, this is alpha, because all of these part has to be 180 degrees, and it happens only if, and this is known that 90 degrees, this part has to be alpha, this part has to be 90 minus alpha, because this triangle has also 180 degrees inside. Okay, basic geometry class, yeah? I will not stop on it. So I can take this off. It's just for basic understanding. So if these parts are alpha, I definitely know that this is a tension force, maybe tension force 1, tension force 2. They are not equal to each other because it's important direction where it rotates. We know that our chain is spinning, or our cylinder is spinning at a certain direction, something like this, or probably this, and the horizontal tension forces might not be the same. Yeah, they might not be the same. However, we definitely know if this is T cosine alpha, this is T cosine alpha. If it is T1, if it's T2, okay, this is not a problem. But we definitely know that tension force inward, yeah, tension force vertical is the same from all the sides. This is just T sine alpha, this is just T sine alpha. It doesn't matter. Why? Because if I take this small part again, yeah, this small part again, its vertical axis is exactly the force which is pulling us inward. And I can definitely say that all these parts of, if I take any part of this chain, they're pulled inward with the same force. So we cannot say that this force, yeah, this force acting on this part of dm is larger than this force. It cannot be larger. It will not be larger. So it's the same force which is acting inward from all the sides, yeah, centripetal acceleration. So it's the same for all the parts which are just dm, 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 and dm, and dl, of course. All of them have small masses and small lengths, of course. Okay, yeah, this part, let me call this is dl. If this part is dl, definitely I know that this part is just dl divided by 2, this part is dl divided by 2. Why is this important? Because we right now need to identify one thing. Yeah. So this is T sine alpha, right? This is T sine alpha. They are equal to each other. We have proved it. And they are forces which are pulling us inward. So let's write down here Newton's second law. This is very important and very universal law, very helpful law. This is the net force equals mass multiplied acceleration. Okay, this is good. This is good. Okay, so what are the forces? We can write it for both vertical axis and horizontal axis. For vertical axis, we definitely know that dmg is pulling us downwards and friction force is opposing us, and this might be dma. But there is a problem to it. What is the problem? What is the problem? As I've said before, this acceleration, yeah, this is acceleration is 0. Why? Why acceleration is 0? What's the problem? Because it just starts. It's going to accelerate downward, but it still didn't. It is at the very instant, at the very last moment, where it's going to slip. So this word, if, it has very big meaning. If this thing reaches angular velocity 4 radians per second, the chain slips off, but the chain is going to slip off. This is the most important part. Okay, so but still, at the very last instant, acceleration is 0, so it's going to become more than 0. It's going to increase, but it still didn't. That's why we know that this thing is entirely not just dma. Yeah, if this is dma and a is equal to 0, this all part is equal to 0. It means that I can write it like this. This is just 0, and it means that if I move this thing here, it will become just positive. So it's going to be something like this. dmg equals friction force. And also I know that the static friction and kinetic friction, there are two types, and we know that static friction, static friction and kinetic friction, mu, the difference is that in kinetic friction, F friction K, it's exactly mu n. Mu n. In static friction, F friction static, it's smaller or equal to mu n. Where is it equal to mu n in static friction? When this friction force static goes maximum value, it's going to become mu n, and this is logical. So as it in its last moment where it's maximum, when it's going to become kinetic friction, it becomes mu n. It just turned mu n, and then it's totally becomes kinetic friction. But at its last moment, it's just equals to mu n. It's not less. Okay, so this is really important. This is really important to understand. Okay, so what can we do with this? We can say that dmg equals mu n. Okay, this is really important because it is in its last moment where it's going to go, and static friction is as at its last limit. Yeah, it's the maximum static friction. That's why we can say that it is mu n. Okay, so what else? If we look at this, yeah, we have proof that the force which is pulling us inward, it's 2 tension sine alpha. Yeah, because we have 2 of them, this one and this one. So we have 2 of them and they're equal. That's why I can write it 2 sine alpha. And 2t sine alpha. Oops, 2t sine alpha. So a lot of people might ask me why just 2t. There are a lot of tension forces. This. Yes, logically it is correct, but as I've said you before, as I've told you before, we have small part of dm, and it is pulled from 2 sides. Yeah, that's why we just consider only its 2 sides, this part and this part, and that's why we have only 2t sine alpha. Okay, good. So if our centripetal acceleration goes inward, AC, and 2t sine alpha is the same direction we write it first. It's got to be 2t sine alpha minus, because normal force acts against it, and it's equal to dmac, right? Because it must be small dm. We are working with small dm, and AC is important because it's centripetal acceleration. This is something important to note. It's not just a regular acceleration, it's centripetal acceleration, which is dm, and centripetal acceleration has its own formula, which is v squared divided by r, and we know that v is equal to omega r, and if we put it right here, it's going to become omega squared r squared divided by r. We can cancel one r, and we will have something omega squared r. So our centripetal acceleration will become just this thing, omega squared r. Okay, omega squared r. This is really important. Okay, so we have already this formula, yeah, this one. So we can find here what we were meant to find. It's the coefficient of friction, mu. And in order to find this mu, we can just write it here like this. Mu equals what? dmg divided by n. And we can find n from here, right? Let's move it here. Let's move this part here. And then we will have something like this. N will be equal to what? 2t sine alpha minus dm multiplied omega squared r. Okay, good. What is the problem with 2t sine alpha? We don't know sine alpha because alpha is the angle that we just theoretically put there, yeah. But however, we know this is a triangle, and we know that sine alpha is just opposite divided by hypotenuse, and we know both of those things. Sine alpha is going to be just dl divided by 2 divided by r, because dl divided by 2 is opposite, this is hypotenuse, okay? And then it is going to become just dl divided by 2r, okay? Good. Let's put it here. N equals 2t. Now it's dl divided by 2r minus dm multiplied omega squared r. Okay, good. I can get rid of this 2. Oops, sorry, this 2. Good. And I have a problem, in fact. I have here dm, which is, I don't know this dm. I have dl, I also don't know this dl. And I have this dm. Okay, but what can we do? We can write this dl with dm. Yeah? I will show you how, but first, why do I need it? If I write this dl with dm form, I can take dm inside of this dl, take it outside, and if I take it outside, I can cancel it with this dm mathematically, and this is a good idea. Okay, let's try to do it. How we do it? In fact, if small dm is responsible for dl, and m is responsible for large L, which is just 2 pi r, because we have that r, we are given with r, yeah? So, we also have here omega. We shouldn't forget about that. So what can we do? We know that the relation between these two things is equal to the relation between these two things. So that's how we can write dm divided by m equals dl divided by, let's write 2 pi r, yeah? And if I write dl with dm, it would be something like this. dl equals what? 2 pi r multiplied dl divided by m. Oops, not dl, it's dm. Yes, of course. Sorry, yeah, something like this. Okay, let's try to write it here. Let's try to put it here. At the top, we've got what? T dl divided by r minus dm omega squared r. Okay, but I know dl right now. I can put it in, and I will have something like this. So yeah, n equals what? T divided by r here. dl is my 2 pi r dm divided by m minus dm omega squared r. Okay. Yeah, good. What can I do with it? What can I do? I think that, yeah, I can get rid of one of these r's, in fact. What else? I can take this dm outside, so basically it becomes something like, you can see this common factor, this dm and this dm. I can take them out. And it will become something like this. Yeah, it's comfortable for us to take dm out, and inside I will have only what's 2 pi t divided by m minus omega squared r and brackets closed. Okay, if I put this n inside here, yeah, I will find my mu. Let's try to do it. Mu equals what? Mu equals dmg divided by n. Am I correct? Yes, I am. Okay, if I put this n inside, it will be just dmg. Yeah, let's put it a little bit here, and let me bring all this answer. I will not write it again. I will just put it inside of inside of n, and then, as I've told you before, we can just cancel these dm's, and then we've got our answer. Yeah, that would be the very answer that we need. Our mu will be equal to what? We have g at the top. We have 2pt, 2 pi t divided by m minus omega squared r. Yeah, we can put it. Yeah, we might not put it inside the brackets. However, let's do it something like this. Let's multiply this thing by m as well, this thing. And then we've got something like this. This would be g at the top, 2pt minus m omega squared r. And we have m at the bottom, totally, right? But by math, we can move it upward, and our answer will be something like this. mg divided by 2 pi t minus m omega squared r. And I believe this is the correct answer. So we have mu, and what? We are given with m. Yeah, this is given. This is 100 grams. Radius is there. This is mass, radius, tension force. We need to find coefficient of friction, and also angular velocity is right here, right? So we are given with mass. We know g is constant, 2 pi is constant, tension force is given, mass again, angular velocity is 4 radians per second we are given, and radius is also given, 20 centimeters. Yeah, so I believe this is the end. Yeah, we don't need to put numbers in because they might vary. The most important part is just physics, and maths is for the rest. Yeah, so this part is our answer, and I believe this is the end. Yeah, if you have any questions, you can write me privately, and this is the end of the video. Yeah, thank you. Goodbye.